going to be reading in Synergetics Explorations in the Geometry of Thinking, sections 400.44 to 400.54. The MITE may be turned inside out by having each of its two A modules and one B module turn themselves inside out and recombine to fill all negative space. It is also to be observed that one all negative space filling and one all positive space filling MITE may be face associated structurally to produce yet another single minimum system asymmetric tetrahedral all positive and negative space filler whose modular volumetric unity value of 6 corresponds with the 6ness of vectorial edges of the minimum system's tetrahedral 4 foci event relationships. So let's take a closer look at what's going on in this paragraph. Here is the MITE that I have. It's made of an A module, a reflection of an A module, and a B module. It's in this set by Till Anderson. It's called a MITE, and it's an asymmetrical tetrahedron. Now, the MITE, each of these components can be turned inside out. Inside out is drawn here in another book by Bucky called Cosmography, where you can see the triangle being inverted or turned inside out on the left. So the MITE may be turned inside out by going through that process for each of its components, the two A modules and the one B module. And then it becomes a negative space filler. 45. It is characteristic of a single prime system that the aggregate of angles convergent around its vertexes must be concave or convex with respect to the position from which they are viewed. Concave if viewed from the inside, convex when viewed from the outside. There are in all systems the additive twoness of the poles and the multiplicative twoness of the coexistent concavity and convexity of the system's insideness and outsideness. Fuller consistently returns to the number 2 because Euler's equation has a plus 2. No matter how many sides a polyhedron has, it's plus 2. And so, rather poetically in a way, Fuller ascribes this 2 to what happens if you rotate any figure. And he will say often that everything is always rotating in some sphere of reference. So that plus 2 refers to the two poles that you create. The multiplicative twoness comes from when you create another edge. So here there's 3 triangles joining at a point, then there's 4. Here's the numbers, and there's 5, then there's 6. When you join one multiplicatively, you end up creating a lot more. So when we go from 3 to 4, we have 8. When we go to 4 to 5, we have 20. And so that's the multiplicative aspect. When you have a system, there will be just the additive twoness. You will have a twoness necessitated because the system will have poles, and you will have a multiplicative twoness depending on how many sides the system has. Planet Earth is a system. You are a system. The surface or minimally enclosing environmental relationship of any system such as the Earth is finite. Other characteristics of systems. Prime rational integer characteristics. Electromagnetic frequencies of systems are sometimes complex but always exist in complementation of gravitational forces to constitute the prime rational integer characteristics of physical systems. Fuller likes to oppose gravitation with radiation. Systems may be symmetrical or asymmetrical. Systems are domains of volumes. Systems can have nuclei and prime volumes cannot. To illustrate the idea of a nucleus, so here's a drawing from elsewhere in Synergetics, but you can see the nucleus is significant, and then we've drawn edges or vectors radiating from the nucleus to the outside surface, as opposed to this diagram. There is no nucleus. So Fuller is reminding us here that sometimes it will be significant for us that the system has a nucleus, and sometimes it'll be significant that it does not, and the prime volumes do not. 2 more sections to read today. Interconnection of Systems. Before we jump in, I'd like to show you this diagram first from Cosmography. So here's a drawing of 2 tetrahedra, and they're associating by a vertex or an event foci. This is very flexible. You can imagine if these were fastened, this guy would be wiggling all over the place and have tremendous freedom. We can then move and imagine that things are associated by an edge. If these two same tetrahedrons, the same shape, but if they were locked by their edge, then they would just be able to wiggle or hinge against each other. They would have less degrees of freedom. If we then associated them by a face, all three, then you would understand that then it would become completely rigid and they would not have any degrees of freedom in relationship to one another. Keep that in mind as we read this section. If two adjacent systems become joined by one vertex, they still constitute two systems, but universally interjointed. That was the single unit joining that I showed you. If two adjacent systems are interconnected by two vertexes, they remain two systems interlocked by a hinge. That's if they're joining on an edge. If two adjacent systems become adjoined by three vertexes, they become one complex system because they have acquired unit insideness and outsideness. We could also say they have acquired structure and they behave as one system. If two adjacent systems are interpositioned with their respective centers of volume congruent and all their respective vertexes equidistant from their common center of volumes, they become one system. So that's a fourth state where they are completely overlapping. If their respective vertexes are at different distances radially from their common center of volumes, they become one complex system. If the complex systems' respective interposition systems are all symmetric, then they become one complex symmetric system. That concludes today's reading in the Systems section of Synergetics. Thanks for joining.